Hello and welcome to The Space Above Us, Episode 75, Space Shuttle Flight 8, STS-8. Challenger hauls the mail. Last time, we rode along on STS-7 as Challenger deployed a couple of comsats and took STS-1 out to play. The free-flying satellite expanded the shuttle's capability envelope by proving that it could handle proximity operations with another spacecraft, a critical skill for future satellite retrieval and repair missions. The historic mission also expanded the social envelope, marking the first time that an American woman flew in space, in the form of Mission Specialist 2, Sally Ride. And to cap it all off, Challenger posed for the STS-1 camera and came home with the first public photos of the orbiter in orbit. Today we'll be talking about, you guessed it, STS-8. I promise my insistence on listing both the shuttle flight number and mission number will make sense in, about 2 missions, but for now just bear with me. STS-8 has a variety of different tasks on tap, so let's just get right into it. Riding all the way in the back of the payload bay was a spacecraft named the Indian National Satellite, or Insat-1B for short. As you may have guessed from the B in the name, Insat-1B was the second in a series of Indian satellites. Similar to the Anik series or Palapa B1, Insat-1B would serve as a major element in the communications infrastructure of a nation, namely India. But Insat-1B provided more than just communications and television service. It also included meteorological equipment, including a high-resolution radiometer, which would allow the Indian government to generate more accurate weather forecasts. The spacecraft was manufactured in California and would be kicked up to GEO by a PAM-D upper stage. If you're curious where Insat-1A is, it turns out that it was launched a year earlier, but ended in mission failure due to a bulky reaction control system. Yet another reminder that space is hard. Originally sharing the payload bay with Insat-1B would have been another spacecraft with a B suffix, TDRS-B, the second spacecraft in the TDRS constellation. But as you'll recall, the upper stage for TDRS-A had a little whoopsie and left the spacecraft in a lower than desired orbit. Engineers on the ground were able to coax TDRS-A into its proper orbit after a lengthy maneuver campaign, but if the orbit had been a little wonkier, they could have just lost the very expensive spacecraft entirely. So while they figured out how to fix the upper stage, TDRS-B was put back on the shelf to wait for a different ride to space. We'll be discussing TDRS-B again, among other things, when we get to the mission it finally launched on, STS-51L. So instead of TDRS-B, when we look in the back of Challenger's payload bay, we find what appears to be some sort of half-baked attempt at a TIE fighter. It's not a half-baked attempt at a TIE fighter, but it sure looks like it. The Payload Flight Test Article, or PFTA, was a specialized device intended to help test the capabilities of the remote manipulator system, the shuttle's robot arm. Imagine 2 large circles connected by a beam, all of which is wrapped in white material. See why I compared it to a TIE fighter? On board the PFTA were no attitude control systems, cameras, thrusters, sensors, or really anything. It's just a big dumb 3,400 kilogram barbell. So why are we launching it into space? Well, I'll talk a little bit more about it once we're on orbit. Another notable payload wasn't in the payload bay, but rather in the middeck. And we've actually seen it before. Remember the Continuous Flow Electrophoresis System, or CFES? This was a device that used some neat electrical tricks to separate particles that had been all mixed up. Well, I haven't mentioned it, but CFES has actually flown a few times already, with this marking its 4th flight. Electrophoresis is a common process on Earth, but with normal Earth gravity, there's only so much you can do with it. It turned out that by doing it in the microgravity environment of low Earth orbit, they could separate orders of magnitude more particles. The reason I mentioned CFES this time is because up until now it's been separating relatively simple particles like proteins. But on STS-8, it would be working on actual living cells. This is all in furtherance of the goal of evaluating medical and pharmaceutical technology in microgravity, which had the potential to spawn a whole new industry. Also on the middeck was a small self-contained module that played host to 6 rats. The rats weren't doing anything, they were mostly just there to enjoy the ride so that they could be examined afterwards. This way the rat enclosure could be checked out before any important experiments depended on it. Fun fact, in order to keep the rats hydrated, they were provided with raw potatoes to nibble on. And on the engineering test side of things, STS-8 would be making use of TDRS-A, which had been renamed TDRS-1 now that it was safely ensconced in geostationary orbit. For the most part, the mission didn't actually need to use the TDRS system, but STS-9, the next flight, would rely heavily on the communications satellite. So STS-8 would be putting the spacecraft through its paces. And lastly, at least for us, were the postal covers. I don't know what it is about NASA and postal covers, but they always seem to be a thing. I believe the last time we talked about them here was in the context of the Apollo 15 scandal, but from what I can tell, space and the mail seem to be weirdly intertwined. What I'm building up to here is that in Challenger's payload bay, crammed into 8 getaway special canisters, were something like 260,000 postal covers. This was a joint venture between NASA and the US Postal Service, which would be splitting the proceeds. After the flight, you could just buy these things from the post office for a little over $15, or about $38 2019 dollars. I found that especially interesting because they already had some special $9.35 stamp on it, which apparently means that by my math, flying them on Challenger only increased their value by 64%. There are actually so many of these things out there that they're not all that hard to get your hands on. If you hop on eBay, you can find flown covers for as low as like $10. I bought mine yesterday just in case you all go nuts and they all disappear. Commanding the mission would be the only non-rookie of the flight, Dick Truly. Since that means we have 4 other crew members to introduce, I'll keep it brief once again. We last saw Truly flying as pilot on STS-2 as well as the approach and landing tests. This is his second and final spaceflight. But if you miss Truly, don't worry, he'll be named the NASA Administrator in 6 years, so I'm sure we'll be hearing from him again. Flying next to Truly in the pilot seat was Dan Brandenstein. Daniel Brandenstein was born on January 17, 1943 in Watertown, Wisconsin. He attended the University of Wisconsin, earning a bachelor's degree in mathematics and physics in 1965. Just to sort of put that in space timeline context, if we assume he graduated in the spring of that year, he was getting out of school between Gemini 3 and 4. But Brandenstein wasn't flying in Project Gemini. Instead, he joined the Navy, who taught him how to fly jet planes, specifically the A-6 Intruder, which sounds like a very rude aircraft. He eventually found his way to the U.S. Naval Test Pilot School in Maryland, but rather than hopping right into a spacesuit, he returned to Navy duty aboard an aircraft carrier. In 1978, he joined NASA along with 34 of his fellow astronauts. This is his first of 4 spaceflights. Mission Specialist 1, flying on the flight deck for ascent and entry, was Guy Bluford. Guy on Bluford was born on November 22, 1942 in Philadelphia, Pennsylvania. Guy graduated from Penn State University in 1964 with a bachelor's degree in aerospace engineering. Since he was part of Air Force ROTC, he then hopped into pilot training with the Air Force. He learned how to fly the F-4C interceptor jet. He then flew that aircraft through the skies of Vietnam, racking up 144 combat missions, about half of which were over enemy territory in North Vietnam. When he returned stateside, he enrolled in the Air Force Institute of Technology, picking up a master's degree in aerospace engineering in 1974. After that, he apparently hadn't had enough, since he stuck around for another 4 years, earning a PhD in aerospace engineering from the same institution. He joined NASA as part of Astronaut Group 8 in 1978. Guy will be continuing our streak of social firsts, since with this mission he will become the first African American to fly in space. This is his first of 4 spaceflights. Joining Guy on the flight deck for both ascent and entry was Mission Specialist 2, Dale Gardner. Dale Gardner was born on November 8, 1948 in Fairmont, Minnesota. Gardner is the latest in a long line of astronauts I've introduced here who have come from the traditional pilot path. He earned a bachelor's degree in engineering physics from the University of Illinois in 1970 before joining up with the U.S. Navy. The Navy must have been impressed because only a year later he found himself at the Naval Air Test Center as part of the Weapons System Test Division. For his next assignment, he flew the F-14 off of, and more impressively, onto the USS Enterprise. No, not OV-101, the aircraft carrier Enterprise. He too was a member of the astronaut class of 1978, and this is his first of 2 flights. And last but not least, riding all by his lonesome down on the middeck was Mission Specialist 3, Bill Thornton. William Thornton was born on April 14, 1929 in Faison, North Carolina. Thornton attended the University of North Carolina at Chapel Hill, earning a bachelor's degree in physics in 1952. While he was doing that, he was also doing Air Force ROTC, so naturally he joined the Air Force upon graduation. From there, he found himself in a few roles involving aircraft instrumentation, eventually directing the avionics division at Del Mar Engineering Labs in LA. He went back to school, but this time it was medical school. Now Dr. Thornton, he returned to the Air Force as a flight surgeon in 1964. He became increasingly involved in space medicine before becoming an astronaut himself in 1967. One of his main contributions was inventing the device used on Skylab to measure astronaut mass in microgravity, a device still used to this day. One more contribution was his participation in the Skylab Medical Experiment Altitude Test, which again was a 56-day simulation of a Skylab mission using similar equipment to the real thing. Thornton decided that it was his duty to break stuff on the ground so that they didn't break in space. Among the things he broke were the exercise bike and some sort of urine centrifuge, which then sprayed its contents all around the confines of the Skylab mock-up. I'm sure his crewmates loved him for that one. This is his first of 2 flights. Launch day for STS-8 was pushed back 26 days due to the TDRS-B swap-out, and then once the day arrived, it was delayed for a further 17 minutes due to thunderstorms in the area. But when Challenger finally roared off the pad on August 30th, 1983, it was well worth the wait. That's because the local time was 2:32 a.m., marking the shuttle's first night launch. I've never seen a shuttle night launch in person, but I have seen the launch of a Falcon 9, a much smaller vehicle, and it was indescribable. So I can only imagine how awe-inspiring it must have been to see night turn to day as Challenger tore a path through the Florida sky. For those wondering why Challenger had to launch at 2:32 a.m. and why rockets seem to have a weird habit of requiring extremely specific and inconvenient launch times, that's just how the orbital mechanics worked out. If Insat 1B had such and such a requirement, which meant that Challenger needed to be in such and such an orbit, and that they wanted to deploy on Rev 27, then you rewound the clock and discovered that you're launching at 2:32 a.m. Hope you took a nap. On board, the crew had trained with the night launch in mind. They had practiced in darkened simulators, strategically positioning lights so that they could easily read their checklists, and they took measures to protect their night vision. And then the solid rocket boosters ignited, and that plan went right out the window. It turned out that the SRBs were so bright that from the point of view of the folks on the flight deck, it may as well have just been daytime. Oh well, lesson learned. After an uneventful ascent and ohms burn pair, Challenger arrived in its nominal orbit. The first big event of the mission was the deploy of Insat 1B. The spacecraft used the now familiar to us PAM-D upper stage and associated support equipment. So when the time came, the sunshield was opened, Insat 1B was spun up, and the crew commanded the explosive bolts holding it to the orbiter to fire. Springs in the support equipment gently pushed on Insat, which gently drifted out of the payload bay and into the distance, spinning all the way. One item of note with this deployment was that the mission anomaly report states that about 20 seconds after separation, an object was observed departing the payload bay. This object came very close to Insat 1B and might have even impacted it. According to the anomaly report, the spacecraft later had some difficulty extending its solar panel array, potentially due to contact with this mystery object. I was actually able to find video of the deployment, but it cut off a few seconds before the object was spotted, and I was unable to find the referenced investigation report. The NASA Technical Reports Server, NTRS, is a wonderful resource, but it doesn't always have everything, and it doesn't have the world's greatest search engine. Maybe next time. In a sign of how the upcoming TDRS tests would go, Mission Control was forced to radio Challenger and wake up one of the crew in the middle of the second night. That's because the telemetry link had gone down and Mission Control was unable to fix it remotely. After losing 3 hours of experiment data, the unlucky crew member reset the connection and went back to bed. I was hoping this would be one of those stories where I could tell you how I spent like 40 minutes tracking down exactly which crew member it was because I just needed to know. But instead, I spent like 40 minutes failing to track down exactly which crew member it was. So pick your favorite, I guess. On day 3 and 4, the mostly well-rested crew's focus was on payload flight test article exercises. Again, the PFTA is a big, heavy thing that looks like a barbell or a TIE fighter, depending on where you land on the nerd spectrum. And since you're listening to this podcast, I'm just going to go ahead and assume that you're going with TIE fighter. Anyway, the PFTA didn't do anything. It was literally just a big, heavy 20-foot by 15-foot thing with a bunch of grapple fixtures and some lead ballast. So why launch an 8,500-pound lump into orbit? Because in upcoming flights, the remote manipulator system was going to be handling some pretty massive payloads. A lot heavier than the relatively lightweight stuff handled so far. Even SPOS-01 was only around 5,000 pounds. The Hubble Space Telescope, not quite on our radar yet, but useful as a touchstone, is nearly 5 times that. So it was important to determine the handling characteristics of the robot arm under a heavier load. And I would imagine that the thought process went something like, if we're going to have a problem with the arm, let's have it with a useless payload instead of suddenly discovering halfway through deploying something important that we're in trouble. Over the course of 2 days, the RMS would grapple the PFTA, move it around, and exercise all of the RMS joints. And in a further stress test of the system, the orbiter's attitude control thrusters would be blipped a few times with the PFTA on the end of the robot arm to see how well it handled forces with such a heavy load attached. Thankfully for the robot arm engineers, everything went great. One other interesting thing about the robot arm on this mission was that for the first time it was sent underneath the orbiter. This is a pretty delicate maneuver since the arm needs to reach outside of the payload bay, around the fuselage, and down near the fragile thermal protection system. For the first time, astronauts could see, through the RMS camera, the vast number of black tiles on the underbelly of the orbiter while in space. I thought this was noteworthy because after STS-107, sending the RMS down under the orbiter to inspect the thermal protection system would become standard operating procedure. So it was interesting to see them trying it out this early in the program. While the PFTA tests were happening, work was also underway to test the connection to TDRS-1. TDRS uses a bunch of different connection types. For example, the lower bandwidth S-band and higher bandwidth Ku band. S-band is fine for stuff like voice or basic telemetry, but for video or downlinking lots of science data, you needed Ku band. And Ku band is tougher. It requires very accurate pointing of a special antenna, and that needs the ability to track the TDRS satellite it's communicating with. Unfortunately, as noted on Night 2, the connection was a little wonky. But there was good news and bad news there. The bad news was that they had, in fact, found a real problem. A problem that would need to be addressed quickly before STS-9 could fly. The good news is that the problem was not with TDRS-1, or with the orbiter systems, or the new antenna. It was with the ground software at the TDRS downlink station at White Sands, New Mexico. If you're gonna have a problem somewhere in a space system, the ground software is probably the best place to have it. It's easier to throw more computer resources at it, and it's less tricky than trying to update the software on the spacecraft itself or hardware on the orbiter. Ground software often passes unnoticed by most folks, even space nerds. But speaking as someone who has now spent the last few years writing ground software, I can tell you from first-hand experience that it really can make a big difference in how well a mission runs. So, dropped connections are a problem, but when the connection was up, TDRS was great. High bandwidth and long communications passes would completely change the way on-orbit operations were run. The crew even took advantage of the strong signal to do the first in-flight press conference since Apollo 17. After 5 days in orbit, Insat 1B deployed, CFIS cells separated, PFTA wiggled around, and TDRS tested, it was time to come home. I guess since TDRS is being a little wonky, it probably makes sense to stay in orbit for one more day to keep working on testing that all-important system a little bit more. Alright, everyone good? Great. After 6 days in orbit, Insat 1B deployed, Cephas cells separated, PFTA wiggled around, and TDRS tested, it was time to come home. After a 139.5 second deorbit burn, Challenger began descending towards the upper atmosphere. Today's destination would be Edwards Air Force Base again, but with a twist. Since the crew was already getting experience on night operations with the launch, why not make the landing at night as well? So that's why after 6 days, 1 hour, 8 minutes, and 43 seconds, Challenger came cruising in over bright xenon floodlights surrounding the runway at Edwards, touching down in the middle of the night at 12:40 a.m. STS-8 was a success, deploying yet another satellite, expanding the known capabilities of the orbiter with the PFTA tests, and paving the way for the science-driven STS-9 to follow. But after the flight, a distressing discovery was made, which served as a reminder of just how high the stakes really were. At the base of each solid rocket booster is a massive nozzle. The nozzle funnels the hot gas from the burning propellant out of the SRB casing and can steer side to side to help orient the stack. To keep the nozzle safe, it is covered in a 3-inch thick ablative lining. Its job is to take the punishment from the incredibly powerful SRB exhaust so that the nozzle doesn't have to. Normally, this lining wears down from 3 inches down to about 1.5 inches over the course of powered flight. After the flight of STS-8, though, the SRBs were inspected and it was discovered that the lining had burned down to only 0.2 inches thick. 1.5 versus 0.2. It's tough to estimate these things, but experts suspect that the lining was something like 14 seconds away from wearing away entirely, which would have led to a nozzle rupture, which would have led to asymmetrical thrust between the two SRBs, which almost certainly would have led to the destruction of the orbiter. For this flight, the lining held, the shuttle arrived in orbit, and 6 days later the mission ended in success. But it was a scary close call. The problem was eventually traced to one bad batch of the special material used to make the nozzle lining, which caused some minor delays as other SRBs had their nozzle linings replaced. Spaceflight will never tolerate carelessness, incapacity, and neglect. Next time, it'll be time to give TDRS a proper workout as part of STS-9. Space Shuttle Columbia flies again with John Young at the helm and an extraordinary experimental platform in the payload bay. So join us as we get Skylab deja vu and explore the first flight of Spacelab. Ad Astra, catch you on the next pass.